Greetings. One thing I want to impress upon everyone is how many different exponential technologies there are and how many functionalities have exponential progress because computation, storage, and other core accelerating technologies are in fact progressing at such a rapid rate. And yes, it's true that computational gains are saturating because we are in the dying stages of the old paradigm of computation and are waiting for a new paradigm of computation, and there's several competing technologies that could be this new paradigm. But putting that aside for a second, just consider the exponential growth of computation and how many other functionalities are enabled by it. Very few people realize that telescope power rises exponentially because of computational progress. Very few people are aware of this at all or realize it or have any curiosity about what that really means. But I take you back to an article that I wrote way back in 2006. So we're talking 15 years ago. And this article is in the description box below, of course. But the title is Telescope Power, Yet Another Accelerating Technology. And you can go all the way back to the time of Galileo, which is more than 400 years ago, where with his primitive telescope, he discovered the moons of Jupiter. A few decades later, Christian Huygens discovered the rings of Saturn. And planets like Uranus and Neptune were not even discovered or otherwise recognized as planets in the former case until much later because telescopic power was still only progressing at a very slow speed. However, the reason that telescope power rises exponentially in the age of computing is because an image is really just data, and therefore resolution of the image as well as transmission of an image is a functionality of data management and data processing. And therefore telescope power increases as a square root of computational progress. Now, I have a video in this card over here about why that's exactly the same reason that video game graphics improve at the rate that they do, is because to have the dimension of each pixel, you need to have 4 times as many pixels as this image here shows. Therefore, the speed of improvement of video game graphics or telescope power is a square root of the speed of computational progress, which is still very fast. If Moore's law was a doubling every 18 months and therefore a quadrupling every 36 months, telescope power, just like video game graphics, doubles every 36 months. And therefore we get to various manifestations of exponentially improving telescope progress. One of my earlier videos was how all these errant asteroids that were in danger of hitting the Earth at one time, even as late as the 1990s, we had no way of mapping them or even discovering which ones were nearby and when they might hit. But now, as per this video that I made, and I bring up this chart again, the number of near-Earth asteroids that are discovered and mapped has been rising exponentially. There were very few of them mapped even as recently as 2000, and that's why there were so many movies in the 1990s about some surprise asteroid impact. Now we have mapped all the ones that are larger than 1 kilometer, and those are the very dangerous ones. Most of the ones that are between 140 meters and 1 kilometer, which are much less dangerous but still quite dangerous. And many of the ones that are smaller than 140 meters, which are for the most part not dangerous at all. They would burn up in the atmosphere. And this is an exponential curve. And you can see how little was known even as recently as 2000 versus now in 2021. And therefore, this threat of asteroid impacts has been virtually mitigated because there's no major impact anticipated within the next 15 plus years, and probably not for a fair amount of time after that. And even if there is one that is anticipated after that point, we have plenty of time to pinpoint it and have some mitigation strategy for it. So this was asteroid detection, which does have a direct impact on everyone's lives, since an asteroid impact would disrupt everything about everyone's lives. Now, the advancement of telescopic power also greatly increases the discovery of things that may not have any impact on most people's day-to-day lives, but are still fascinating and of crucial relevance to the future of humanity and the future of all intelligence, and that is exoplanet discovery. Until the mid-1990s, we did not know for sure if other stars had planets around them. We assumed that they did, but we could not verify it. Then the first one was discovered in the mid-90s for sure, and then a couple more were discovered. But it was real news that another exoplanet was discovered. But then the rate started to increase, and this is the cumulative discovery chart. And you can see it's an exponential curve. The big jumps are because certain telescopes, such as the Kepler Space Observatory, publish all their findings in one big shot. So 1,000 exoplanets are confirmed in one shot. But otherwise, we will eventually get to the point of multiple telescopes of multiple types facing in multiple directions, discovering exoplanets. And this exponential trend will continue because it is a function of accelerating telescopic power, exponential telescopic power, which itself is a byproduct of exponential computing. I don't want to say the word exponential too many times in this video, but that is where we see the results here in something that people did not think could become a high-tech process. A telescope is a telescope is a telescope. So why are we so much more capable of discovering exoplanets now than we were in the 1990s? Which was not a super primitive time. It wasn't the time of Galileo, yet we're able to do it. And the methods of discovery are also expanding. As you see from the multiple colors, the legend tells you what type of method of discovery is being used. And now there are almost 5,000 exoplanets discovered at the time of taping this video. Remember, there was a time when there was just 1, 2, 3. Every single exoplanet, which was a once in few months news item, was still mainstream news. Now they don't even report anymore. If we found another 200 exoplanets in the next 90 days, most of you wouldn't even know. And the number that has been found is rising so quickly that ones that are Earth-sized and within what humans would consider the life zone of a star are also piling up in discovery, and now there are many that fit that description. There was a time when we could only detect the very biggest planets that were very close to the star, so absolutely unsuitable for human-like life. But now we find many planets that are potentially Earth-like. And even though we've only discovered 5,000 of the estimated 500 billion plus planets in the Milky Way galaxy, we have the proportions down already. The data pool is large enough to estimate how many are in the life zone of a star, how many are Earth-like, how many are of a certain type, so on and so forth. And that already enables us to extrapolate how many of each type there are in the entire galaxy, even from this early data set. So I have another video about exoplanets specifically because that's a lengthy topic, and it's a very important topic for the future. But since this video is about telescopic power, this is what I want to impress upon you, how profound it is that computational power increases telescope power because, as I explained before, every image is really just data. And more computing means more data can be processed and resolved into an image and transmitted, and therefore posted on the internet for millions of people to download the same image. This is not even the era of library books where you had to go to the library to see some pictures that a probe took of some astronomical phenomenon. And you had to hope that the library you went to had books with the type of pictures that you like. Now you don't even have to bother with that type of uncertainty at all. So I go back to the main article. From 2006, we still had very few images and very few exoplanets discovered relative to what we have today. Only about 100 or so exoplanets were known, even at the time when I wrote this article in 2006. And now there's 5,000. And we're not even surprised to see that number rise exponentially anymore. And that's why the future holds untold wonders, because we're about to see a huge barrage of very high quality astronomical images, and the quality and quantity will continue to rise exponentially. The 2020s will have better and more images than all of the hundreds upon hundreds of years before that point, in which people were even studying astronomy, and the thousands of years even before that, where it was only the naked eye. And the 2030s will have more and better images than all of civilization before the year 2030. And think about that from an exponential point of view. So it's really something to look forward to, and one of the visual manifestations of how exponential computational progress kind of feeds the soul. You see all these wondrous images, the inspiration that people receive, the education that children and adults receive about astronomy, and the ease of access of these images through the internet, as well as the generation of these images through more and more of these advanced telescopes, is really something profound. And that's why the real space age is now, as I also explained in this video in this card up here. Exciting times lie ahead. Now, if you like this type of content, I encourage you to subscribe to this channel, and thank you very much for watching.